Dear students, today we will be discussing about testing of liquid flatbed collector and its application. So, this testing of flatbed collector, there are three standard procedures for testing, okay, which is suggested by ASRE. Okay. ASRE is nothing but American Society of Heating, Refrigeration and Air Conditioning Engineers. Okay. The essential requirements for all the procedures are: number one, arrangement for the inlet of fluid at constant temperature with flexibility to set different values of the inlet temperatures, pyranometer to measure the solar radiation on the surface of the flatbed collector, then provisions for recording of mass flow rate and different temperatures has to be there. Then equipment for measuring pressure and pressure loss across the LFPCs need to be attached. Then why this testing is required? Because standard testing and rating procedures provide an equitable basis for comparing the efficiency of different types of collectors and an essential basis for their selection for a given applications as well as their design improvement. Okay. Now, let us discuss how this solar flatbed collector can be tested, okay, with a standard protocol. So, what figure is shown here is a setup for characterization of a flatbed collector. So, it composed of a flatbed collector which need to be characterized, a liquid pump, a heat exchanger with a cooling coil, then storage tank, of course bypass valve is also required, and flow meter. Of course, to know the inlet fluid temperature and outlet fluid temperature, we must have some kind of temperature sensor. Okay. This is temperature sensor or thermocouple. Okay. This is for TFI and this is for TFO. Of course, we need anemometer for wind speed. One anemometer is required, anemometer, and pyranometer for solar radiation, which is global solar radiation, okay, and rotameter for flow measurement, right. So, what happens? We need to perform experiments at fixed values of mass flow rate and TFI, okay, and we need to do the experiment at different days, okay. So, what is the purpose of this heat exchanger? Because we need to provide controlled amount of fluid through the collector at particular temperature, okay. So, in order to control this temperature, we need to arrange this assembly, okay. So, we have to cool this fluid what is coming out from the collector, and then if it is lower than what is required, then we need to heat it, okay, by using electrical means. So, in this storage tank, one electrical heater is attached, so that this fluid can be heated to a particular temperature, okay. And this bypass valve is attached to control the amount of flow which need to be flows inside this flatbed collector, right. So, this measurement recorded in each data set are fluid flow rate, fluid inlet and outlet temperature, okay. We need thermocouples, here we need some kind of rotameters, solar radiation incident, so we need pyranometer which gives global radiation falling on that particular place, ambient temperature, of course we need one thermometer or maybe one temperature sensor, and wind speed we need to know. So, for that we need to have a anemometer, okay. So, once we have those equipment or instruments, we can measure all those parameters, okay. So, these two assembly, like combination of the heat exchanger and the storage tank, with an electric heater provides a means for adjusting and controlling the inlet fluid temperature to the collector to a desired value, right. So, what is required for inlet, that has to be controlled. Okay. By using this arrangement, we can control the temperature and we can feed the temperature to this flat plate collector, right. The testing standard specifies that the collector shall be tested under clear sky conditions to determine its efficiency characteristics. Okay. On a given day, data is recorded under steady state condition for fixed values of mass flow rate and fluid inlet temperature, right. So, what is steady state conditions? So, a collector is considered to be operating under steady state conditions if the deviation of the experimental parameters is less than the following specified limit over a 15 minutes period. Okay. So, this variation of global radiation incident on the collector should be in this range plus minus 50 watt per meter square, and ambient temperature should be in the range of -1 to +1 degree C, and fluid flow rate is plus minus 1%, and fluid inlet temperature variation should be plus minus 0.1 degree C, and temperature rise across the collector should be in the range of plus minus 0.1 degree C. Okay? And also this IT value, the total radiation which is falling on the collector, should be greater than 700 watt per meter square, and this wind speed should vary from 2 to 5, okay, and this fluid flow rate should be 0.02 kg per second per square meter of the gross collector area. So, this has to be controlled, and this arrangement or this measurement is valid for both indoor and outdoor testing. Okay. In indoor, of course, we need a solar simulator for testing, right. Now, for fixed values of mass flow rate and fluid inlet temperature, equal number of tests to be conducted before and after solar noon. Okay. So, that is at 11 o'clock, 11:30, 12:30 and 1 or 1300 hour LAT, which is solar time or local apparent time, right. And also any bias due to transient effect is eliminated, okay, during the test procedure. The tests are to be performed at 4 inlet temperatures on different days. Minimum of 4 days is required to characterize a flat plate collector. Okay. So, hence a total of 16 data sets are obtained, right, if we perform for 4 days during the time mentioned here, right. Now, if I am interested to know the efficiency of the collector, then straight away you can use this expression, eta I is QU by AC into IT, right. So, QU is the useful heat gain, AC is the collector area, and IT is the total solar radiation which is falling on the collector, right. And QU is nothing but M mass of the fluid which is flowing, and Cp is the specific heat of the fluid, then fluid outlet temperature minus fluid inlet temperature to the collector area into IT, right. Also, we know the famous equation for measurement of useful heat gain, which is given by Hotel-Wheeler-Bliss equation. Okay. So, this QE is equal to FRAP in bracket S minus UL TFI minus TA, right. So, this expression QU is related with TFI. Okay. If we know the fluid inlet temperature and ambient is known, and if other values are known, then straight away you can calculate what will be the useful heat gain. Okay. Now, we will relate this to efficiency. Because of that, we need to do something. So, we divide this expression by AC into IT. Okay? Then what happens here? QU by AC into IT is equal to FR AP and this bracket term divided by AC into IT. Okay? So, we can bring this side here, then it will be AP by AC, of course, FR will be multiplied, then this expression will be something like this. Okay? Also, this S can be expressed something like this here. So, IT into tau into alpha average. So, it includes both beam and diffuse radiation. So, when we talk about average values of transmissibility and absorptivity, right. So, on substitution of this S is equal to IT multiplied by tau alpha average, then what we will have? So, this expression will modify to something like this. Okay. So, tau alpha average minus UL TFI minus TA divided by IT. Okay. Now, for a particular collector, this FR, tau alpha average, UL are constant. Okay. So, if we see then, and this part is constant always for a particular collector. So, this will be constant here. Okay. So, this will be something like y is equal to mx, okay, minus c, or I can write c minus mx. Okay. So, c is nothing but this constant part here, okay, and m will be this multiplied by ul will be m and x will be this part, right. So, this will be a some kind of straight line with negative slope, right. So, if we plot it, then what will happen? So, we will get some kind of this kind of plot. Okay. So, if we tell this is y axis and this is x axis, okay. So, this intercept is nothing but this value. Okay. So, this intercept will give the value of this part and the slope will give this part. Okay. So, for a typical case, so we will get an expression something like this. Okay. So, we will explain how this can be generated. So, this will be the expression, right. So, this is something like a straight line equation with negative slope, right. So, let us take a commercial FPC, say this is the characteristics curve for a commercial FPC having single cover and selective copper absorber plate with area of the collector is 2.27 square meter and mass flow rate of 0.0456 kg per second, right. So, if we use this, then we will have this kind of configuration, okay, and this least square yield will give this straight line fitting equation. Okay. So, these expressions we can get from this scatter data. So, we will get lot of data. So, if we have a draw a trade line, then we can generate this kind of equation, right. So, if we compare this equation with the earlier what we have described just now. So, this AP by AC for a collector is given as 0.909, and if we use this information for calculation of FR tau alpha average, then it will be something like this. Okay. And also FR UL we can calculate. So, this will be about 4.427 watt meter square Kelvin. So, this is how we can calculate the value of FR tau alpha average and FR UL, right, once you know this intercept and slope. Okay. Now, for liquid flat plate collectors, changes in mass flow rate do not appreciably affect the performance because of the relatively high value of liquid side heat transfer coefficient. And for this reason, although the efficiency curve of a collector is determined for a particular value of mass flow rate, it can also be used for predicting the behavior of the collector for other flow rates which differ a little from the value used during testing. We will demonstrate how this can be done in a numerical example. Also, sometimes we are interested to know what will be the performance of a flat plate collector over a day. Okay. So, this data was taken from a book solar energy principles of thermal collection and storage by Sukhatme and Nayak. So, what it is shown here, the variation of efficiency with time. Okay. What you can see, as the time increases, so efficiency is increasing first. Okay. So, at noon it is maximum and then it is decreasing, right. So, here also you can see here how these efficiencies are first increasing with time and then reaches a maximum value here and then decreases, right. Also you can see here other values. Okay. So, this ut is also decreasing, right. So, this variation was plotted with an assumption that water flow rate, then water inlet temperature, ambient temperature and wind speed are not varying during that time. Okay. So, what we can conclude here, with increase in solar radiation, that efficiency can be improved. That is what it is demonstrated in this slide. Okay. Now, let us take a numerical problem. So, it goes something like a water heating flat plate collector is fitted with 2 glass covers and a non-selective absorber plate of dimension 1/2 meter. The collector is tested by the standard procedure and the following data is obtained. Okay. So, tau alpha average is given, mass flow rate is given, Cp of water is given and Ac by Ap is given. Okay. Now, we need to calculate the values of instantaneous efficiency and plot these against the parameter Tfi minus Ta divided by It. Then we need to draw a base fit straight line and determine the values of UL and Fr. Okay. Again in the second case, how does the values of Fr sense if the value of mass flow rate is increased to 1.3 kg per minutes. Assume that the value of F dash does not change significantly because of increase of mass flow rate. Okay. So, let us solve this problem. So, given values are here. So, straight away you can use this expression Ac by Ap is given as 1.2, hence Ac is equal to 1.2 into Ap, which is nothing but 1.2 into 2 into 1. So, it will be 2.4 meter square. Okay. And under testing conditions, this eta I can be calculated by using this expression Qu by Ac It, right. And also we know this is nothing but m Cp dt is nothing but Tfo minus Tfi. So, first I will show one simple calculation, then I will move to this generation of straight line fitting. Okay. So, this simple calculation by using first set of data which is given in the exercise. So, for first set what is given in the problem. So, Tfo is given as 93.98 degree, then you have Tfi is 84.95 degree, okay, and Ta is given as 23 degree. Okay. This can be seen here. So, this data I am talking about. So, Tfo is 93, then Tfi is 84, then Ta is 23 and I is 885. Okay. So, It is equal to 885 watt meter square. Okay. So, now using this expression, then eta I can be calculated. So, m is how much? 1.1 minute. So, 1 by 1 divided by 60, it will be kg per second. Then Cp value is 4.18 into 10 cube, which will be 4.18 kilojoule. So, we have converted to joule, and what is the temperature difference is 93.98 degree TFO, then TFI is 84.95 degree. Okay. And then we will have AC and IT. AC is already we have calculated, which is equal to 2.4, and then IT is 885 for this first set of data. So, it will be, so if we multiply it by 100, it will be in percentage. So, it will be 32.58 percentage. Okay. So, now I will show how for all the values eta I can be calculated by using a spreadsheet. Okay. So, let us click here and let us learn how this can be generated. Okay. So, here, so what we need to do, F naught minus F I. So, what is F naught here? So, I will use this. So, this is F naught minus we have F I. Okay. So, this will be something like this. So, if we drag it, then we will have something like this. Okay. And then what we can do, this divided by IT. Okay. So, this divided by IT is here. Okay. So, I can take this value and we can expand it, okay, for all the calculations, right. And for calculation of eta I, so this part if we substitute m and then multiply with Cp and divided by AC, then this will be something like this for this case. Okay. So, for all the calculations this will be fixed, right, mCp divided by AC. So, here what happens, what we have learned. So, this m into Cp divided by AC. So, this part is constant for all the values, right. So, here what happens, we can straight away calculate this value. So, this 31.93 we have star or multiply by this part. Okay. So, we can give enter and it will be the efficiency values, not in the percentage, okay, in the fraction. And here also we can calculate. So, this value we can calculate. So, once we know TFI, what is TFI here? This is the TFI, then we have to deduct minus TA, then divided by, so this will come outside, divided by, we will have IT. So, this is D and then we have this value. Okay. So, this is TFI, then we will have TA, then IT. Okay. So, I can use this. So, this will be, I can drag it something like this. Okay. So, now we need to plot this versus this. So, I will take this data out from this calculation sheet, then I will paste it here, which is number, and here I can paste, and then we have these values. Okay. So, now these two, because this will be in the x axis and this will be in the y axis, right. So, we can plot it, here. So, this is the plot, and again we can add the trade line and we can get the equation, display the equation and R square value. Okay. So, the equation is something like this here. Okay. So, as you can see, this part is nothing but intercept part and this is the, this part is slope part, right. So, what we have done, we have generated the trade line or say this fitting line, okay, and we can use this equation for calculation of FR and UL. Okay. So, this equation is required now, right. So, now we will go back and see how this can be calculated. Okay. So, here what I can write is the expression what we have got there. So, this eta I is something like minus 2.9467 TFI minus TA divided by IT plus 0.538. Okay. So, this is known to us now. Now, also we know the expression for eta I when we use Hotel-Wheeler-Bliss equation. So, this FR AP by AC is tau alpha average minus UL, then TFI minus TA divided by IT. Okay. So, if we, this may be equation 2, this may be equation 3. If we comparing equation 2 and 3, we have this 0.538. So, this part is intercept is equal to FR AP by AC tau into alpha average, right. So, if we substitute those values, what we have, straight away you can calculate what is FR value, or maybe we can simplify FR, which is equal to 0.538 into AC, okay. Then you have AP tau into alpha average, okay. And if we substitute those values, so AP by AC is, this is something like it will be 0.538, then we have 1.2, and then tau alpha average value is 0.74, which is given in the problem. So, if you substitute, then we will get a value of something like 8724. Okay. So, FR value is found to be 0.8724, right. So, now our next calculation will be for UL. Okay. So, overall loss coefficient, how to calculate this overall loss coefficient? So, we can use this part. Okay. So, FR multiplied by AP into UL, which is equal to this part. Okay. So, this part is equivalent to this part, okay, when you multiply this part, okay, and this part is actually this part. Okay. Now, if we calculate UL, then we have to use this expression FR AP by AC into UL, which is equal to 2.946, right. So, if you substitute these values of FR, so this UL will be 2.946 divided by FR AP by AC. Okay. So, this is the value here. Okay. So, if we substitute these values, then what we will have, UL will be 0.533 watt meter square. If it is in Celsius, then Celsius. Okay. So, UL value we have calculated. So, this is the solution for the first part. Solution for the first part. So, what is the next part? So, next part, again we need to calculate FR value if we sense our flow rate is increased to 1.3 kg per minutes. Okay. So, again we will go back to this spreadsheet, and already I have done this calculation for this case. So, similarly these equations are known, only change will be this part 37.735, this part will be there. Okay. So, here once we use those calculated value and then use in this calculation, then we will get this kind of values, and for TFI minus TA to IT we will get these values. And if we take out these two and then plot it, then what we will have this kind of plot, and then our equation will be something like this. Okay. So, similarly if we do the calculation, then we will get these values. Okay. So, in our earlier case it was also about 0.8724. Okay. So, it is almost constant. So, even though this mass flow rate is varying, but this FR is not changing. Okay. That is why in case of liquid flat plate collector, only single mass flow rate is enough to characterize the entire flat plate collector. Okay. So, there is no point of doing the characterization at different mass flow rates. Okay. But in case of solar air heater, experiments are need to be performed at different mass flow rates. Okay. Because heat transfer coefficient in the air side is much lower than heat transfer coefficient in the liquid side. Okay. So, we got a very close value of FR. Okay. Now let us solve one more problem. So, this problem is something like a liquid flat plate collector has the following characteristic parameters. FR tau alpha is given, FR UL is given. So, here AP by ACs are same. Okay. So, this is 1. Okay. So, there is no variations are considered. Normally AC is about 1.2 times AP. Okay. Sometimes we can represent this instantaneous efficiency in terms of mCp dt in terms of I into AP also, right. So, this can also be represented in terms of plate area, right. So, it is operating under following conditions, like solar flux incident on the collector plane is 900 watt per meter square. Water flow rate is given as 0.015 kg second meter square of the absorber area. Ambient temperature is 20 degrees C, inlet water temperature is 40 degrees C. So, now we need to calculate the mean absorber plate temperature of the collector if the collector efficiency factor is given. So, F this is nothing but F this is given to us, okay, and we need to calculate what is TPM, okay, mean temperature of the absorber plate, right. And second question, if the circulating pump fails, what is the maximum temperature attained by the plate? Okay. So, it may so happen that temperature rise is very high. So, under that condition your material may damage. Okay. For that condition we need to find out what will be the maximum temperature if that circulation pump is not working. Okay. So, we can use this expression for calculation of different parameters. So, we need to calculate TPM, okay, and then maximum temperature, maximum Tmax or Tmax PM also we need to calculate. Okay. So, now let us start this solution. Okay. So, here we know this expression eta I. First I will write this eta I. So, eta I is nothing but FR. So, it is assumed that AP and AC are same. So, you have tau alpha average minus FR UL, then TFI minus TA divided by IT, right. And if we substitute those values, because FR tau alpha average is given to us, FR tau alpha average is given and then FR UL is given. So, straight away you can use those values here. So, it is 0.68 minus 6.1 into this temperature difference is 20, then IT is 900. what is given in the problem. So, this eta I is found to be 0.544. Okay. This is eta I, or efficiency of the collector. Okay. We can also find out what will be the TFO. So, once we know this instantaneous efficiency, we know this eta I is MCP TFO minus TFI divided by AP into I. Okay. So, if you substitute here in all those values, so this will be 0.544 and M is given here. So, what is the M? 0.015. So, this is something like M by AP. Okay. So, this is M by AP is given as 0.015 kg second meter square. Okay. So, we can put a dot here because it is a flow rate. So, this value is given. Okay. So, this value is 0.015 and this TFI is given as 40 and I is 900. So, on substitution what we can calculate is TFO, which is found to be 47.8 degree Celsius. Okay. So, this can also be calculated. And also we know the expression for FR, what is given in the last slides. Okay. This is the expression for FR. So, we can write this expression FR. So, this FR is something like M CP, then you have UL, then AP, right, and then this is 1 minus exponential of minus F dash UL AP divided by M dot CP. Okay. So, now we need to find out what is FR. Okay. So, UL we can represent, or we can omit this UL here, already we know the value. So, what value is known to us? FR UL is equal to 6.1, then UL will be 6.1 divided by FR. Okay. So, we can use this here. Okay. So, then what will happen? M dot AP is known to us, then UL will be FR. So, this CP will be there, FR will be here, and then we have 6.1, right, and then similarly this expression also sends. So, minus F, this value is known to us, it is 0.9 and UL is nothing but 6.1 divided by FR. Okay. And CP value is known. Okay. So, this is CP I can write. So, CP is nothing but 4.18 into 10 to the power of 3. Okay. And multiplied by M into CP. Okay. So, this value is also known to us. So, this is AP and then we have M. Okay. So, these values are also known to us. Okay. So, if we substitute and this FR and this FR goes off, okay, then what we will have once we simplify it. So, we will get something like 0.9 is equal to exponential of something like minus 0.0875 by FR. So, we can calculate what will be the FR by taking ln, okay, or log. Okay. It will be 0.83. Okay. So, once we know FR, now we can use the other expression. So, QU is equal to FR AP, okay. Then we have tau into alpha, okay, into I or IT, then we have UL TFI minus TA. Okay. Or we can simplify QU by AP is something like FR tau alpha, this is average because it includes both beam and diffuse radiation, then IT minus UL, so DFI minus QA. Okay. So, this expression QU is in terms of TFI. Okay. So, this expression I can mark as 1 maybe. Okay. And for FR tau alpha average is equal to 0.68, and from here we can calculate what is tau alpha average. Okay. So, 0.68 to what is FR value here is 0.83, which will be equal to 0.819. Okay. And again we can calculate what will be UL. Okay. FR is known, and so if we substitute FR value here in this expression, so we can calculate what will be UL. Okay. So, UL we can calculate, which will be equal to 7.349 watt meter square. What's the unit here? Let me see. Yeah, we can just Kelvin. Okay. Sometimes it is in Celsius also. Okay. So, UL we know now, tau alpha average is known to us. So, this is known, and TFI is known. Okay. So, from that we can calculate what is QU by AP. Okay. So, now equation 1 implies QU by AP on substitution of these values. So, we will get a value of 498.01 watt per meter square. Okay. Because all values are known to us, TFI is known, TA is known, IT is known, these are calculated now. So, we can use this, FR is known. So, we can straightway calculate what will be QU by AP or heat flux, right. So, once we know this, again we can use the equation, this equation for useful heat gain. Okay. So, if we use that equation, QU by AP is equal to I tau into alpha average minus UL TPM minus TA, right. So, if we substitute the value of QU by AP 498.01 is equal to IT is known 900, and the tau alpha average is known now 819, and UL is also known 7.349. Now, we need to calculate what is TPM, and TA is also known to us, its value is 20. Okay. Right. So, on calculation we will get TPM value is equal to 53.8 degrees C. Okay. So, this is the solution for first part. Okay. Right. So, now we have calculated what will be the mean temperature of the absorber plate if the characteristics parameters are given for a particular collector, right. Now, our next step is if the circulating pump fails. Okay. So, pump will circulate there, and then if circulating pump fails, okay, there is no useful heat gain. Okay. So, under that condition, if there is no useful heat gain, so in the second part of the problem is useful heat gain, or QU is nothing but useful heat gain, okay, which is equal to 0. And already we know what is the expression for QU, which is nothing but AP into S minus UL AP TPM minus TA, because we need to find out what will be the mean plate temperature if that circulation pump fails. That means, what will be the maximum temperature we will get in the collector if no heat is collected. Okay. So, this QU is 0 and here APS minus same term UL AP TPM minus TA, right. So, if we simplify, we will have this is APUP is common for both the expression. So, we can take out S this part, and S is nothing but tau into alpha average into IT, and this will be something like UL TPM minus TA. Okay. So, this we can calculate now. Okay. What will be these values, right? Something like already we know FR, what is we know FR is 0.68 by tau alpha average. Okay. And of course, we can use what we have calculated, but independently also we can solve this 6.1 by UL, right. Then by using this, so since both the expressions same, so 0.68 by tau alpha average is equal to 6.1 by UL. So, from here we can calculate tau alpha average by UL is nothing but 0.68 by 6.1, which is equal to 0.111, right. So, if we simplify further, this will be UL multiplied by IT plus TA will be TPM, right. So, if we substitute these values, so what we will get TPM will be about 119.9 degree, okay. So, which is equal to 120 degree C, right. So, this is TPM. So, this maximum temperature what we will get is 120 if no heat is collected from the collector on the particular day. In earlier case, what we got TPM was 53.8 degree C. Now, you can see the rise in temperature. Okay. So, this is the maximum temperature which can be seen if no heat is collected from the collector. Okay. So, I hope that you understand the way we have solved these two problems. Okay. So, this has got a lot of practical applications. So, that is why this problem has been discussed in this class. Also, let us discuss something about applications of liquid flat plate collector. Okay. There are multiple applications of liquid flat plate collector. So, namely indoor swimming pools, nowadays it is quite common. So, people are using solar energy for heating water in the swimming pool. Okay. So, water heating is a primary concern. Milk pasteurization also this is seen application of flat plate collector, and power generation for low temperature. Okay. Power generation, this kind of systems are used. Drying, then solar water heater for biogas. So, it is seen that if we maintain certain temperature by using some kind of heat inside the biogas plant, then of course, we can maximize the biogas production. So, this nowadays solar collectors are used to circulate fluid inside the biogas plant to get maximum biogas generation. Then slurry drying is also one of the applications of liquid flat plate collector. So, here two examples we have shown. In the first example, use of solar energy for indoor swimming pool. What you can see, this is the collector. So, number of collectors required will be decided based on the capacity of the water to be heated. So, collectors will be installed normally at the rooftop or maybe some kind of structure, and then hot water will be pumped through filter, and this will be circulated in the swimming pool. Again it will pump back, again it will flow through. So, it will work in a closed loop. Okay. So, if we consider this is the inlet, this is the outlet. So, after it will go through this and then it will move this way, and then after this heat loss is taking place, then water has to be circulated. So, this is the circulation loop. So, this will work in a closed loop, and this figure shows the application of liquid flat plate collector for power generation. So, we have this liquid flat plate collector. So, hot water is generated and this is also working in a closed loop. So, pump will be there. So, water will be circulated, it goes and heat exchange will be there. So, this is a heat storage tank. Okay. Again, we need to have some kind of heat exchanger, so that the amount of heat what is generated that can be provided to other working fluid. Okay. And that working fluid will move in a circuit, that is also in a closed loop, and this working fluid is different and it will evaporate at low temperature. Okay. And this will expand. Okay. Vapor will expand in a turbine and then energy will be generated, and remaining it will condense in a condenser and it will pump again through this heat exchanger and it will work in a closed loop, right. So, of course, we need some other devices like cooling tower, okay, because this has to be cooled. Okay. So, this is an assembly. So, here ORC is used. So, ORC is nothing but organic Rankine cycle, because organic fluid is used, because of that it is known as organic Rankine cycle. So, here hot water at temperature around 100 degrees C is stored in the thermal storage tank. So, here about 100 degrees C, no, the water temperature which is stored in this tank, and then low boiling point working fluid vaporizes at vapor generator at around 90 degrees C and leaves the condenser at 35 degrees. So, here at 35 degrees C. Okay. So, this will be maybe 90, 95, some losses will be there. So, maybe 90 degrees C. Okay. So, that way, even though Carnot efficiency is very low, still sometimes this configuration can be applied for generation of small amount of power. This expansion will be there from 90 to 35 here. Okay. So, this working fluid normally use R11, R13, R114, then methyl chloride, etc. Okay. So, having low boiling point. Okay. So, this is also working closed loop and this is also working closed loop. We need to have a heat exchanger to exchange the heat what is generated via this flat plate collector, and then it is expanded in the turbine and electricity is generated, and then rest is condensed and then it is circulated again and again, right. So, in this presentation we have learned details about testing of liquid flat plate collector, what is the need of liquid flat plate collector testing, and then how this can be tested, and we have solved very interesting problems to strengthen the understanding how this liquid flat plate collector can be tested, and we have also learned the applications of liquid flat plate collector. Okay. So, thank you very much for watching this video.